In our research, we concluded that recurrent multi-stage fusion network was a successful method to comprehend multimodal language. RMFN uses intramodal interaction and cross-modal interaction. Intramodal interactions are the interactions within each modality. Cross-modal interactions are the interactions between each modality. RMFN decomposes the fusion problem into multiple stages. Each stage is focused on the subset of multimodal signals for effective fusion. RMFN decomposes the multimodal fusion problem into multiple recursive stages. To evaluate RMFN, 3 domains of multimodal languages were researched for data: multimodal sentiment analysis, emotion recognition, and speaker traits recognition. Multimodal sentiment analysis involves analyzing speakers' sentiment based on video content. For example, opinion segments from online videos were annotated for sentiment from -3 to 3. Multimodal emotion recognition involves speaker emotions based on verbal and nonverbal behaviors. For example, segment of dialogues were annotated for the presence of human emotions such as happiness, sadness, anger, and neutral. Multimodal speaker traits involves recognizing speaker traits based on multimodal communicative behaviors. For example, movie review videos were annotated for 12 speaker traits such as confidence, passion, pleasant voice, credible, vivid, expertise, reserved, relaxed, thorough, nervous, persuasive, and humorous. This diagram displays the recurrent multi-stage fusion network. The multi-stage fusion process has 3 modules: highlight, fuse, and summarize. Signals from each modality is represented with an intramodal recurrent neural network. Each intramodal recurrent network outputs a unimodal representation. RMFN process fuses all these unimodals together into a cross-modal representation. These concatenated intramodal networks outputs can be seen in these annotated variables. To review the specifics of the modules, highlight module identifies a subset of multimodal signal. Fuse model performs local fusion before integrating with previous fusion representations. Summarize translates the representation at the final stage into a cross-model representation to be fed back into the intramodal recurrent networks. Lastly, each stage in this figure varies from 1 to k. 1 represents the initial stage, while k represents the final.
The results of RMFN on different datasets are very interesting. This network improves the passing tree algorithms for happy, sad, and angry emotions, but not for neutral emotions. Neutral expressions are idiosyncratic. Facial morphological features influence the neutral expression. For example, some people may always look angry. In this example, he delivers a lot of intensity can be inferred as both positive or negative sentiment and thus is ambiguous in its intent. But on observing the corresponding language and acoustic modality, presence of smile and phonological emphasis is noticed. These nonverbal behaviors resolve ambiguity.
Multimodal sentiment analysis is a new dimension of traditional text-based sentiment analysis, which includes other modalities such as audio and visual data. RMFN is highly effective in modeling human multimodal language. In addition to achieving state-of-the-art performance, comparisons show that the multiple stages coordinate to capture both synchronous and asynchronous multimodal interactions. Companies and research labs have combined all these tools to accurately estimate public opinion and significantly improve marketing strategies. Thank you.